Hello, here we consider moving from a single population variance to two population variances and doing inference on those two. In particular, we are interested in comparing two population variances. And this is a common situation that the need to compare, let's see here, the need to compare two population variances or two standard deviations. For example, if you had two processes that were developing different products, and you were interested in is the tolerance of one, how does it compare to the other? Are they tighter? Is one tighter than the other? This sort of thing. Comparing two standard deviations is a common sort of test to want to do. And also another major application for the test of equality of two population variances is checking to see if this assumption for the pooled t-test is valid. Okay, so that's sometimes called a pre-test on the pooled t-test. Okay, so in this context, we compare two variances by looking at their ratio, sigma 1 squared over sigma 2 squared. So this is different than when we were comparing two population means. If you recall, comparing two population means, we looked at their difference. We could have looked at their ratio, but we knew something nice about the point estimator that that estimated that difference. It turns out the point estimator that estimates the difference between sigma 1 squared and sigma 2 squared is not very clean, and so we're going to work with the ratio there. Okay, and the natural point estimator for the population variances, or for their ratio, is the ratio of their sample variances. Okay. And what we're going to look here at is the sampling distribution of that ratio. All right. Recall, in order to use y bar, we needed to know something about its sampling distribution to do inference on mu. And in the same way, we need to know something about the sampling distribution of the ratio of the sample variances in order to do inference on the ratio of the population variances. Okay? Here's a theorem that gives us insight into that. The theorem starts off, there's two samples here. Now, I've got one sample of size n1, another sample of size n2, and they are independent, this is important, random samples from normal distributions. That's also important, with means mu1 and mu2. If those assumptions are met, then this theorem tells us that this particular quantity here, s1 squared over sigma 1 squared divided by s2 squared over sigma 2 squared, that follows an F distribution Now this is a new distribution, and we'll explore it in a little bit. But this F distribution, it has two parameters that govern its shape, and they're called, one is called the numerator degrees of freedom, and the other is the denominator degrees of freedom. So let me write that out here. This ratio follows an F distribution with numerator degrees of freedom equal to n1 minus 1, and denominator degrees of freedom equal to n2 minus 1. Okay. Well, let's look at the F distribution. So let's take an aside here from the inference procedure. Let's look at this particular distribution. This is a continuous distribution, so it has a probability density function. And this here is the mess of the PDF for what's called an F distribution. Very complicated. It involves a lot of stuff that we're not going to get into in this course, but I just want to present it to you. Know that this is kind of what's going on in the background, and this is the curve that is giving us the percentiles that we're going to need later on. I do want you to take notice, though, that the this F distribution, or this distribution, lives where x is greater than or equal to 0, and also it's determined by these two values here. That's a Greek letter nu 1 and nu 2. Nu 1 and nu 2 are called the numerator and the denominator degrees of freedom. Okay, let me back up. I'll just make note of this. This is called a gamma function. It involves an integral, which is an idea from calculus. If you haven't seen this, don't worry about it. Not a big idea, but if you have taken a calculus course, then here's a connection with a calculus course that you may have had in the past. Okay. The compact notation that we're going to use to say a variable follows an F distribution is this one here. The first entry is going to be the numerator degrees of freedom. The second entry is the denominator degrees of freedom. Alright, so we're going to make use of that shorthand notation. The graph of an F distribution, here's several graphs rather. For differing degrees of freedom, D1 is the numerator degrees of freedom, and D2 is the denominator degrees of freedom. It's generally right skewed. It's always in the it's always for non-negative values or for values greater than or equal to 0. That's how we look at the F distribution. This just if you want to, you could go online and find an F distribution calculator and adjust the degrees of freedom and and study how the shape changes. For us right now, I'm not that interested in that. I just want you to see that, hey, it's a right skewed distribution typically, and that it is determined by its degrees of freedom, both numerator and denominator. The F distribution has little or no modeling applications. I've never seen a modeling application for it, a probability modeling application. But it does have a lot of applications in statistical inference, most notably in testing the equality of two variances. That's what we're doing in this lesson, and also in what's called analysis of variance, which we will see later. An F random variable is constructed by taking the ratio of two independent chi-squared variables and dividing by their respective degrees of freedom. In other words, F is a chi-squared variable. There's the chi-squared over its degrees of freedom, and then we take the ratio of that over another chi-squared over its degrees of freedom. Okay, that's usually where an F variable comes from. Lower tail percentiles are obtained from upper percentiles by using this relationship here. F sub 1 minus alpha is df1 comma df2 is equal to 1 over f of alpha df2 comma df1. And what I want you to notice here is that the degrees of freedom are switched. And so that's a nice property for the F distribution. If you switch the degrees of freedom, you are moving from what was an upper tail percentile to now to a lower tail percentile. So the degrees of freedom are switched. What we're going to do most of the time is use the F distribution to find percentiles to build a confidence interval or to run a hypothesis test. It is kind of a different animal, this F distribution, so let's get a little bit comfortable with it. The percentiles are found in Table 8 of your book in the appendix, and I want us to get just some practice in finding a few of those percentiles. So first here, I've got two problems here. First, I want to find an F variable. F's a 0.05. So you recall the subscript on a percentile denotes the area under the curve to the right of that percentile. So this area there is 0.05. Okay, and of course this area then would be 0.95. So I want this, and this is for numerator degrees of freedom 8 and denominator degrees of freedom 6. Okay, so I'm going to go to Table 8 here in our book. There's the chi-square table. I'm going to go to Table 8. Here's Table 8. It gives for degrees of freedom 1 and degrees of freedom 2. You notice here it's 1, 2, 3, 4, 5, 6, 7, 8, up to 10 for degrees of freedom 1. And the degrees of freedom 2 goes from 1 to 6. And what this table gives us, if you look at this picture here in the right corner of upper right corner, it gives us the upper tail percentiles. And so we're looking here for F's a 0.05. Alright, so we're looking where alpha is 0.05 and degrees of freedom 1 is 8. So we are in, I'm trying to highlight that column. We're in that column there, the column with the 8 on it. Come down to degrees of freedom 6 for the denominator. Let me make sure I'm reading that right. Yeah, for the denominator degrees of freedom 6, and I'm looking for 0.05, and so here that value, I'm trying to circle the cursor around it, is 4.15. So if we go back to our notes here, this is 4.15. Alright, that is the F distribution, or we would say it is the 95th percentile, or the upper percentile for an F distribution with 8 numerator degrees of freedom and 6 denominator degrees of freedom. Okay, moving on to this next one here. In this one we want to find F.95. Well, what is that? F.95, draw again the picture here. My degrees of freedom are 9 and 12. F.95 is going to be in the left tail. Notice that subscript is pretty large there, 0.95. The area under the curve to the right of that value is 0.95. And the area under the curve to the left of that value is 0.05. Okay, so we need to find this thing. Well, the table in the book does not give upper percentiles for the F distribution. It does not give lower tail percentiles for the F distribution. So it only gives upper tail percentiles. And so I need to go to the book, go to the table, and find the corresponding upper tail, use this relationship to get that lower tail percentile. So that relationship there is going to tell me that F.95 with 9, 12 degrees of freedom, that's what I want, is actually 1 over F.05 with 12 numerator degrees of freedom and 9 denominator degrees of freedom. Okay, so if I can find that, so that's 1 over, if I can find that, then I've got that lower percentile of interest. So I'm going to go to the F table, 12 numerator degrees of freedom, 9 denominator degrees of freedom. So let's scroll down here. There's 12 numerator degrees of freedom, 9 denominator degrees of freedom. Let's see here. I'm trying to get degrees of freedom 1 is 12. There's 12 right here. And then 9 right here. So I am at alpha is 0.05. So this value is 3.07. So I'm going to go back here to my notes. Here I'm going to have 3.07. And if you, I'm about out of space here, but if you do the computation for this, you'll get 0.326. Okay, so this lower tail percentile is 0.326. All right, a little bit of work to get percentiles for an F distribution, but be comfortable with your textbook and finding these percentiles. You can also find percentiles using Excel or JUMP or some other statistics package, but be comfortable with the table in the book as well. Okay, so now let's come back to inference on the ratio of the population variances. So we developed the F distribution. Let's come back to the inference situation at hand. Suppose we want to do a confidence interval for the ratio of the population variances. Well, the assumptions here are similar or are the same as the assumptions on the previous theorem, that we have 2 independent random samples from normal populations. Okay, so if those assumptions are met, then a confidence interval for the ratio of the population variances is, the lower bound here is S1, the ratio of the sample variances, times FL. FL here is a lower tail percentile, okay, which can be gotten by an upper tail percentile, and you take its reciprocal, and you be sure to switch the degrees of freedom. Notice, just be real careful here, notice these degrees of freedom are switched compared to those. Alright, so I'm going to take those marks off there so you can see it clearly. And then the upper bound for the confidence interval is the ratio of the sample variances times F sub u, and F sub u is the upper tail percentile on the F distribution. Okay, now let's see, so that's the confidence interval for the ratio of the population variances. If you want a confidence interval for the ratio of the standard deviations, you just take the square root of those endpoints there for that interval. All right. Now let's move to a hypothesis test situation. So I'm not going to work through an example. Let's move straight to a hypothesis test for the ratio of 2 population variances. Again, the assumptions are the same here, 2 independent random samples from normal populations. And I could do a two-tail test. I could check to see are the 2 population variances the same, let's see here, or are they different? Okay, notice that the alternative hypothesis for the variances being different is equivalent to the ratio of the variances not being equal to 1. Okay, and also the null hypothesis would be equivalent to the ratio of the variances being equal to 1. This is a reason we use the ratio. We can use the ratio and still judge if one's bigger than the other, or if one's if they're different in some. If they're different from each other. Also, I want us to note here that this can act as a quote-unquote pretest, and I made a note of this already earlier on, for the equal variance assumption. In the pooled t-test. Okay. Some statisticians have problems with doing a lot of pre-test before a main test. Their reasoning usually deals with they don't want to inflate an overall type 1 error. Some use it anyway, but I just want to make it known to you that this could be a pre-test for the pooled t-test. Another testing situation here would be what we're calling a right-tailed test, that sigma 1 squared is bigger than sigma 2 squared. Now, we're not going to present a left-tailed test. We don't really need to. If you want to test this sigma 1 is less than sigma 2, just switch the subscripts, just switch the designation of what you're calling population 1 and what you're calling population 2. That allows you to make any left-tailed test look like a right-tailed test, and the rejection region in that sort of situation is always in the upper tail of the F distribution. Okay, so what does the test statistic look like in a hypothesis test for two population variances? The test statistic is given by this expression here. It turns out it's S1 squared over sigma 1 squared divided by S2 squared over sigma 2 squared. We had seen that ratio. We had seen that ratio in the theorem before we developed the F distribution. And if we assume the null hypothesis is true, so at this stage if I say if H naught, which is sigma 1 squared equals sigma 2 squared, if that is true, and when you do a hypothesis test, that's what you assume, that the null is true throughout. If I assume those population variances are the same, then basically they go away in this ratio because the ratio of that is 1, and I'm just left with the ratio of the sample variances. Okay? So the ratio of the sample variances is my test statistic. Again, this has a degrees of freedom numerator of n1 minus 1 and denominator degrees of freedom of n2 minus, this should be 1 there. So turn that into a 1. Okay. The rejection region here, if we're in the two-tailed test situation, basically we're going to reject if S1 squared is substantially different from S2 squared. Well, what would reflect that? That would be reflected if the F value is either extremely small or extremely large. Extremely small would be on the distribution of F, that is, it would be less than some lower F percentile, and extremely large would be that it's bigger than some upper F percentile. Okay. The right-tailed test would be, how would we check to see if sigma 1 squared is bigger than sigma 2 squared? Well, we would, if sigma 1 squared was in fact bigger than sigma 2 squared, that would reflect in a sample variance S1 squared much bigger than S2 squared, and so we would reject this null and accept this alternative if the F value is big in some sense, or extremely large, in this case larger than an upper tail percentile for the F distribution. Notice this is an upper tail percentile with just with alpha as the right tail probability, and on these other here it's 1 minus alpha over 2 and alpha over 2 here, so the alpha is split in 2 for the two-tailed test as we've typically done in the past. Okay, here's an example. Hit the pause button, read through it, look at the plots, and try to set up the problem yourself, and then hit play when you want to work, when you want to see me work through it. Okay, so we have two data sets here. We want to compare the two population variances. And I went ahead and gave you the QQ plots of the two data sets, and they indicate that normality is tenable there. Alright, so we're going to go forward with the formal hypothesis test here, and I'm going to look at first, just to make clear, the parameters of interest. first parameter of interest is sigma 1 squared, and it's the population variance of anxiety scores of all hemodialysis patients who viewed relaxation tapes. Okay, so there's variability in the data, and you can look at the data and tell that they're not all the same value. Sigma 1 squared describes that variability for the first population. For the second population, it's the same thing, but this is for patients who viewed ultimately neutral tapes, right? Okay. So this is an effort to reduce anxiety scores over hemodialysis. Okay, so we want to compare here the two population variances, and perhaps maybe this is a side question to the bigger question of interest. Maybe the bigger question of interest for researchers is to see if the mu1 goes with relaxation and mu2 is the population mean with neutral. Could we conclude that mu1 is less than mu2? Is on the average, are the relaxation scores smaller for those that on average are the anxiety scores smaller for the relaxation group compared to the neutral group? And that might be the bigger question of interest within this study, but in order to test that, say using the pooled t-test, you would need to check to see if the population variances are the same. And that's what we're looking at here. And so that's going to set up our hypotheses. The alternative, again, is the claim that we want to test. Do we have evidence that the variances differ? So is sigma squared different than sigma 2 squared? Sigma 1 squared different than sigma 2 squared? That's the alternative. The null is that they are the same. Okay. My test statistic here, I'm just going to go ahead and go with the observed test statistic. It's an F test statistic. Recall this observed test statistic is the ratio of the two sample variances, and up here the two sample variances were given 10.154, 9.197. Okay, so we'll square that, divided by 9.197 squared, and that equals 1.2189. Okay, that's my observed test statistic. Now really I need to check to see, hey, does this fall in the rejection region? And so the rejection region here, we could have done this before the test statistic, but what's the rejection region? It's going to be here. This is a two-tail test, right? It's a two-tail test, so I'm going to reject H0 if either one of those two occur, that F is really small or F is really large. And so I've got to represent that on the distribution here of F. Remember, it's right skewed. Over here I've got F, the subscript 1 minus alpha over 2. Over here I've got F comma alpha over, or F subscript alpha over 2. my alpha specified was 10% or 0.10. So I'm going to split that here and split that here. So this is going to be f sub alpha. So this is going to be 1 minus 0.05. So this is going to be f sub 0.95. And this is going to be f sub 0.05. Okay. Now, so this area here is 0.05. This area here is 0.05. This is an upper tail percentile. Let's find it first, because the table works naturally with upper tail percentiles first. Now the degrees of freedom here, the degrees of freedom, let's see, the degrees of freedom for the numerator, again it's n1 minus 1. There are 31 data points in the first sample, and so that would be 30 for the numerator degrees of freedom. The denominator degrees of freedom is n2 minus 1, and that's 25 minus 1, or 24. Okay, so 30 and 24 is what I need to work with. So let's go look at our table here, 30 and 24. 30 and 24 here. So numerator degrees of freedom 30, there we go, in that column there, and 24. So I'm going to have to scroll down here, 30, 24, and I'm pretty sure it's in here. Here we go, there's 30, and now let's see, make sure I'm in the right column. 30 and then 24. Okay, the upper value is 1.94. That's the upper percentile. So let's go back to our notes here, 1.94. Let's see, we kind of zoomed in, didn't really want to. 1.94. That's that value. Now, this lower f value, again, I'm going to have to do some finagling with the f distribution and another f distribution with the degrees of freedom switch to get this lower value. Remember, f 0.95, the degrees of freedom are 30 and 24, but that's related to, or that's equal to 1 over f sub 0.05, comma 24, comma 30. Again, using that reciprocal relationship. So I'm going to switch the degrees of freedom, look for the upper percentile where the degrees of freedom are 24 and 30 respectively. So I'm going to look for 24 and 30. So here's 24, and then let's go to 30 here. Do I get to 30? Degrees of freedom 24, and then 30 right there, and so I get that percentile is 1.89. So back to the notes here. So this is going to be 1 over 1.89, and if you take that ratio, you get 0.529. So that's what this quantity is here, 0.529. So anything to the left of this is the rejection, in the rejection region, or anything to the right of this is also the rejection region. Alright, so you can see here, where does our statistic fall? Well, it falls well inside or not inside the rejection region. And so we're going to fail to reject the null hypothesis here. So our decision is to, we would say we fail to reject H naught here. And so it's, what does that mean? Let me come back to the hypotheses. So we don't have strong evidence to go from here to here as our statement regarding the two population variances. So that's kind of a weak statement of evidence or weak statement of support that the variances are equal, and some use this as a pretest for the pooled t-test. And so I'm going to make a note of this, that some, not all statisticians, but some might take this as weak evidence that sigma 1 squared is close to sigma 2 squared, and then go forward with a pooled t-test on the difference of the population means there. Okay, we're not going to do that in here. I might make quick note of that on the jump video that corresponds to this, but for now I'm not going to specifically look at that pooled t-test. Alright, moving on here. Quickly, we're going to go through these next 2 pages. I don't want to spend too much time here, but just make you aware of what's going on with in this situation. We can actually look at more than 2 population variances. Alright, and this is a common situation. In particular, it's a common pretest for an analysis of variance situation, which is another procedure that compares several population means, and we'll look at that later on. But anyway, this is a situation to be aware of. We have a couple of tests I'm going to present to you. We're not going to worry about doing any of the mathematics with these. I present some of the mathematics. I'm not worried about it. I just want you to be able to use JUMP or some other package to compute it, and also just to be somewhat familiar with these procedures and their hypotheses, and also the associated assumptions of the procedures. But this first procedure we're going to look at is called Hartley's F-max test, and it's an extension of the F-test that we just discussed, and it requires independent random samples of the same size from, now we have T normally distributed populations. So not just 2 populations, but as many as we want. So we have T populations. And in this kind of test, the hypotheses are given by, well, sigma 1 squared is equal to sigma 2 squared is equal to ... as many as I want, sigma t squared. Okay, that the T variances of those populations are the same. And that's sometimes called homogeneity of the variances. Alright, and if the null hypothesis is not true, that could happen a number of different ways, but the most simple way to state it is that the population variances are not all equal. You could say at least one is different than the others. That would be another way to say it, but they're not all equal. And if that occurs, we have what's called heterogeneity of the population variances. These are special terms that some users of statistics designate when looking at variances: homogeneity and heterogeneity. The test statistic, I'm not going to go into a lot of detail here, basically compares the largest and the smallest sample variances, and there's a particular distribution that goes with that. There's a table 12 here. You can look at that if you want to. I'm just going to let JUMP give me the statistic and an associated p-value and use that. I really want you just to be aware that there's this procedure out here called Hartley's F-max test. It tests the homogeneity of variances, and it has these assumptions in here. Okay? Another kind of test, or another test for population variances is called the Levene's test, sometimes called the Brown-Forsyth test. It actually is numerically a lot more cumbersome. If you look at the form, there's the formula for it. Don't worry about computing that. I just want you to be aware that this is another kind of test. Notice the hypotheses are the same as above, but what's different is that this test does not require the populations to be normally distributed. Okay, and so that's a difference between Hartley's F-max test. Here I'm talking about the rejection region. Again, you don't really need to know that because you're not going to do any of this by hand, so don't sweat that. Just want you to be aware that there's this Brown-Forsyth test that compares several population variances, and there's also the F-max test that does the same thing. Use the F-max test if normality is reasonable for the populations. If it's not, then you're going to go. You would want to look at the Levene's test or Brown-Forsyth test. Okay, so this rounds out the module dealing with inference on population variances.